Welcome to The Explainer. Today, we're jumping straight into a data-driven journey through a realm of physics that honestly looks like pure magic. I mean, if you've ever seen an object just floating in thin air and wondered if we finally hacked gravity, you're absolutely in the right place. We're going to completely unlock the science of levitation by breaking down this incredible phenomenon called the Meissner effect. Get ready, because what seems literally impossible is actually just brilliantly complex physics.
Okay, let's dive into this. What we have here is a solid block steadily levitating, just hovering in midair above a really cold surface, emitting this thick vapor. No strings, no hidden supports, just a physical object resting comfortably on absolutely nothing but a magnetic field. It kind of looks like something straight out of a sci-fi movie, right?
But this forces us to ask a pretty massive question. How is this levitation actually possible? Like, what invisible mechanics are at play to hold that block so firmly in space? Well, that is exactly our mission today. We're going to peel back the layers of this mystery and demystify the hard science, making this apparent magic a reality. To do that, we're going to focus on three main ideas from the data. Idea 1, perfect field expulsion. Idea 2, the opposing currents. Idea 3, quantum locking. And finally, we'll wrap up with the future of superconductors.
Starting off with idea 1, perfect field expulsion.
To really get why that block floats, we got to go back and look at the historical core of this phenomenon, which entirely flipped how physicists view materials. Our story kicks off in 1933. German physicists Walter Meissner and Robert Ochsenfeld were messing around with superconductors. Now, at the time, scientists already knew that certain materials lose all their electrical resistance when you cool them down below a specific critical temperature. But Meissner and Ochsenfeld, they discovered something totally wild, a completely new property. They realized that superconductivity wasn't just about conducting electricity perfectly, it was actually an entirely unique quantum state of matter.
Let's set a baseline here. Think about a material in its normal state versus its superconducting state. When a material is just acting as a normal conductor, magnetic fields can pass right through it, no problem. But the very second it hits that critical temperature and enters the superconducting state, its behavior toward magnetic fields completely transforms.
Which brings up a really fascinating scientific question, one that actually trips up a lot of seasoned physics students. If a conductor has zero electrical resistance, does it automatically behave like a true superconductor? Think about that for a second. If electricity flows perfectly, is that the whole shebang? The answer, surprisingly, is a definitive no. A true superconductor does something an ordinary perfect conductor doesn't necessarily do. When a material becomes superconducting, it actively pushes magnetic field lines out of its interior. It doesn't just let the field hang out in there, it expels it entirely. And we have a specific term for this extraordinary behavior: perfect diamagnetism. It's the complete expulsion of magnetic flux from the interior of a material. This active pushing away of the magnetic field, that is what became known as the Meissner effect. It's the absolute defining hallmark that separates true superconductors from just really good conductors. So the crucial point is summed up perfectly by this simple physics principle: B equals 0. In this equation, B is the magnetic field inside the ideal superconductor. Once you hit that critical temperature, the internal magnetic field is strictly, absolutely 0. The field lines are physically forced to route around the material instead of going through it. Moving on to idea 2, the opposing currents. Right, so we know the magnetic field gets expelled, but how exactly does that physical expulsion happen step by step? Let's break down the mechanics. Step 1. You place the magnet above the superconducting material. Initially, the magnetic field just passes right through it. Step 2. You cool the material below its critical temperature, that's Tc. It officially becomes superconducting. Now, step 3, and this is key. The superconductor generates these tiny, spontaneous surface currents. These currents are the secret sauce. Finally, step 4. Those currents create an effect that violently expels the magnetic field from the interior, and as a direct result of that expulsion, the magnet levitates. The mechanics here are just brilliant. When an external magnetic field tries to penetrate, these induced surface currents literally whip around the edges of the material, and by doing that, they create their own induced magnetic field. The wild part? That induced field perfectly, and I mean exactly, opposes the external magnetic field, pointing in the exact opposite direction and canceling it out inside the material. So to see the final outcome of this invisible battle, compare the normal state to the superconducting state. In the normal state, when it's too warm, the magnetic field lines just slice right through. But when you drop below that critical temperature into the superconducting state, because of those opposing currents we just talked about, the external field lines are completely expelled and diverted. They hug the outside. The interior remains totally clear. That pushing force, that literal magnetic cushion, is exactly what holds our hovering block in the air.
Which brings us to idea 3, quantum locking.
Now, hold on, because it actually gets even crazier. If the Meissner effect blew your mind, this specific iteration of it is going to completely redefine how you think about stability and gravity. To get this, we need to talk about type 2 superconductors. These materials are kind of like a sponge for magnets. They can actually lock magnetic field lines in place within tiny microscopic imperfections in the material itself. So instead of pushing the fields completely away, it traps threads of the magnetic fields inside itself. Because those field lines are trapped, or locked, the superconductor actively resists any change in its position relative to the magnet. This is quantum locking. It allows a magnet to remain stably suspended, not just floating above, but literally locked in place even upside down. It basically ignores gravity entirely. It is for sure one of the most striking and visually bizarre demonstrations in modern physics. The object is fundamentally pinned in three-dimensional space by invisible magnetic threads. Absolutely wild.
And that leads us perfectly into the future of superconductors.
Now, we've seen levitation in a lab setting, but how do we actually apply this to the real world? How do we take these quantum principles and scale them up? Well, this isn't sci-fi anymore. This is applied engineering in action right now. Take high-speed maglev, or magnetic levitation trains. By harnessing the incredible repelling forces born out of the Meissner effect, these trains float above their tracks. And because they never physically touch the track, there is zero friction. This allows them to hit blistering speeds efficiently and incredibly smoothly. It's literally perfect diamagnetism scaled up to move thousands of tons of metal.
Okay, let's quickly lock in our understanding by summarizing those 3 core ideas we extracted from the data today. Number 1, true superconductors don't just conduct. They actively expel magnetic fields, meaning the internal field is 0. Number 2, this expulsion is caused by tiny opposing surface currents that perfectly cancel out external fields, which gives us the force for levitation. And number 3, in type 2 materials, quantum locking allows for incredibly stable suspension, pinning objects in place, even upside down.
Which leaves us with this final thought. We've gone from a hovering block in a lab to high-speed trains completely erasing friction. The data shows us a universe where materials can perfectly manipulate magnetic fields. So I gotta leave you with this. As our ability to engineer these materials at room temperature advances, what previously impossible technologies is quantum locking going to unlock next? The future is floating right in front of us. Thanks for joining me on this explainer, and keep questioning the impossible.